Hello everyone, this is Cameron Snow with Danomics.com. In today's webinar, we're going to be talking about interpretation-ready data workflows and how those can help you reduce your project startup cost. So why is it that you need interpretation-ready data? Well, we did a recent survey of over 100 subsurface interpreters, and over 50% of the respondents said that they spend more than 4 weeks doing data cleanup when starting their new projects, and an overwhelming majority said that they spend 2 weeks or more. So if you think about what this means in terms of cost, it's not just time, it's also money. This would equal out to somewhere around $10,000 in employee wages every time that you start a new project. And so that's why this is so important. So what is interpretation ready data? What do I mean when I say this? Interpretation ready data is data that is ready to be interpreted, so your subsurface professionals can confidently proceed with their interpretation without data quality being their primary concern. So when it comes to interpretation ready data, we're largely focused on non-interpreted data products, so things like well log data, well header data, and production data. And when it comes to things like interpreted data, whether or not that's formation tops or grids or other products like that, those certainly need to undergo a QC process, but the suitability of those data and the accuracy of the interpretation or work product generally requires a different type of scrutiny than looking at the non-interpreted data products. In this webinar, we're going to be focused specifically on well log data. And the reason for that is first, well log data has a large number of challenges associated with it. Second, there is a very specific workflow that we have developed at Danomics to address well log data. And third, the workflow for getting that data interpretation ready is more involved than the workflow for either getting well header data or production data QC'd and interpretation ready. Typically, well header data has already been largely QC'd by vendors, and it's often quite obvious when this data is corrupted or not ready to be interpreted. You either have points that are far outside your area of interest, or you have well bores that are obviously not possible. So it's easy to find the problem data there. With production data, yes, this can be more subtle, but this is data that would undergo a very different QC process as well, and we typically use different methods for that. So this talk is specifically going to be focused on well log data. So when it comes to what interpreters need, I like to think about things in terms of a 4C framework for your well log data. It needs to be clear, consistent, complete, and clean. So the challenges that we have with well log data are twofold. First, log data suffers from several structural problems. So what I mean by this is that just the way the LAS files are made presents several problems. So first of all, we have things like curved mnemonic data. We have data from multiple logging runs. So this can either be logging runs over the same intervals or over multiple depths. Log curves are often presented in different units and in different lithological references. The second challenge that well log data presents are data that are misrepresentative of the subsurface. Now, most of the time, this is either due to washout or badhole conditions, but this can also be due to things like poor digitization of well logs and variations in tool response. And these variations can be caused by either differences between vendors, differences between different generations of tools, and differences in operational procedures like how the tool is calibrated out in the field. To address this, we propose a two-track solution. The first track is dealing with the data attributes, and the second track is dealing with the data quality. So when it comes to dealing with data attributes, this addresses those structural problems that are present in well logs. So we are going to look at curve aliasing, so we can reference everything back to a single name reference. We're going to look at curve units and how we can address those. Then we'll address lithological reference problems to get everything into a common lithological reference frame there. And then finally, we'll look at compositing data together from multiple logging runs. Then when we come back to address log quality, we'll talk about identifying washouts and repairing data that's not representative of the subsurface. And then we'll talk about normalization to remove inconsistencies in our data. And specifically, we only want to focus on inconsistencies that are not driven by the subsurface. So curve mnemonics present quite the challenge. There are around 20 to 30,000 different curve mnemonics. And when you're looking at these, you know, around 100 curve mnemonics will represent about 50% of your data. And if you have around 500 curve mnemonics, you'll cover about 75% of your data. But it's not until you have somewhere between 5 and 10,000 curve mnemonics that you really start to capture 95 to 99% of the available data, which is what our goal should be in most cases. And I will say, in almost all circumstances, it's impractical to expect that you're going to be able to capture 100% of the data because there will often, be 20 or 30,000 curve mnemonics that you'll have to have in your alias table to be able to address that. So curve mnemonics, these vary by vendor, tool type, and tool generation. Often even within the same vendor and the same curve family, you'll often have different tool types available, and those will have specific mnemonics. Sometimes they'll have a high resolution or a low resolution mode, which will create further mnemonics, etc. So that compounds the problem there. I will say that the importance and the scope of these varies quite a bit by curve family. There are certain tools like resistivity tools where you'll see a lot more variation in the curve mnemonics, especially relative to some mnemonics, like let's say an SP curve. So a lot of potential for variation there. And often mnemonics are inadvertently created and propagated out by users. So a user will normalize a curve, and they'll call it GR underscore norm or GR normalized, or they'll perform some type of edit operational curve, and by not using clear practices, they may rename their GR1. That'll then get written to a file, and then you'll have to start tracking that mnemonic as well. So when it comes to curve aliasing to deal with these mnemonics, what it is we're doing is we are essentially establishing a dictionary that software packages can use as a reference. Now, different softwares will take this in different ways. I'm showing you an example from Danomics software here, but essentially we assign an alias, and then we assign a long list of curve mnemonics that tie back to that alias. Before you can do this, you need to determine what are the predominant curve types that you're going to alias. Will this just be the common curve types, or we have a very extensive alias table? And this really depends on what your project needs are. You'll need to think about the level of granularity. So, for example, with something like resistivity, there are obviously multiple depths of investigation. So you have a deep, medium, shallow, and the micro resistivity tools. So at least 4 different types there. But then you may decide you need to be more granular. You may need to separate out your, induction tools from your lateral log tools, for example. With things like, your density curve and your density porosity, you may have, bulk density versus density porosity, but then within density porosity, you may have different lithological references. So you may want to subdivide those as well. And then we also need to determine some order or precedence among the curves. So what happens when we have multiple curves of the same type within a well? Are those, which curve is going to be of higher priority? So those are all considerations that we need to make in the curve aliasing process. And this is typically a very manual process, and it's one that requires a surprising amount of expertise to get correct. You need someone who is familiar enough with the universe of different curve mnemonics that are available. It's going to require a lot of patience because you will have a lot of you'll have a very long tail of potential curve mnemonics that'll need to be addressed if you're going to get that high level of data capture that we want. And you're going to need to revisit this on an ongoing basis. As you're starting new projects and pulling in new data, there will be increasing opportunities for new mnemonics to be present, and you'll need to supplement your alias table for that. The general advice on this, though, is start off as granular as possible, and then as you move into the interpretation workflow, you can start to combine curves into more common names. So, for example, I mentioned a density versus a density porosity. Start off with bulk density, density porosity, sandstone, limestone, and dolomite. Then do the lithological conversion to get the density porosities, then do the conversion to get those back to a bulk density, for example. So those are the type of considerations that need to be made. When it comes to curve units can almost be as bad as mnemonics in some cases. So most of the time, LAS files will have curve units, especially if they are coming from the vendor. However, LAS files can still be valid without curve units. It's important to remember that curve units have their own mnemonics. So, for example, here for the bulk density curve, it's being shown as grams per centimeter cubed, and that's G/C3. That could also be shown as G/cm, G/cm3, grams over cm3. So there are a number of different mnemonics for each of the unit types, so that's something you'll need to explore and consider. Curve units are sometimes wrong. Most often you'll see this when things are reported as percent instead of decimal. But sometimes you may also see things reported in metric or imperial when actually the other is true. And then you can have mixed units. Sometimes within a project you may have some wells that have been reported in metric, sometimes in imperial, or sometimes maybe you'll have some imperial measurements, and some metric measurements as well. So those are things that need to be considered, and you really need to have maybe your own type of workflow for evaluating that. So when it comes to curve units, along a similar line, we have the curve family. So this is when we have the same type of tool, but the vendor reports it differently. So for example, when we have a density porosity versus a bulk density, and this is something I've already mentioned, you may have multiple derivations available. So your density porosity, sandstone, limestone, or dolomite. And even though the conversion may be a simple operation in theory, A lot of times there are a lot of things that go into this. Is the matrix, 2.65 or 2.68 when they list it as sandstone? Is the row fluid 1, 1.04, 1.05, etc.? So there can be some variations in those, and you need to understand the uncertainty that can inject into the data as you move downstream. So as I was saying, we need to have our own workflow essentially to deal with curve units. So what I would prescribe is something as laid out here on the left, where we read the curve name, we evaluate the header. Does that have clearly labeled units? If so, we can perform that conversion. We may or may not want to evaluate the statistics if we think there's something meaningful there, and then we can perform a conversion based on either some type of logic or knowledge of that curve family. So here I have an example of a density porosity curve. So let's just walk through this. So we start off, we have our density porosity curve, which we can tell from d phi, and then the underscore SS tells us that this was measured in sandstone units, or a sandstone lithological reference. The units on this may be percent or decimal, so we need to evaluate that and convert to decimal if we need to. Let's say those units were already in decimal, and we come down here. Now when we look at this, if we see the mean is less than 1, that's probably tells us, hey, yes, that actually is in decimal. So we can go ahead and we can perform the conversion over to bulk density. If not, if we look down here and we see that the mean is greater than 1, that would tell us that it's actually probably in percent, or that we have some nonsensical units. So we could, even though we may not know the units clearly up here, it may become obvious when we look at the statistics. We confirm that conversion to decimal, and then we can perform the conversion to bulk density. And you'll need to think about the logic on this for each curve type and handle that independently. So when it comes to lithological references, vendors often report the same data differently, and this can be very frustrating, but this is just something that we have to deal with. As I mentioned, this can be a simple calculation reference, like is it a density porosity versus density porosity sandstone or dolomite, for example. It can also be a measurement reference. So for example, neutron curves, these can be measured in a limestone, sandstone, or dolomite reference. This is an actual setting on the tool in many cases, and it has to do with how we calibrate that tool. And in general, when we perform the petrophysics, we want this to be in a limestone reference framework. So you may need to do a conversion there. So there will be some areas of uncertainty here. So typically, if you just receive a curve that says either d phi or n phi, we will assume that that is in a limestone reference matrix unless we know otherwise due to either the curve name, so something like n phi underscore SS or n phi underscore dolomite, or from the curve description. So this does open the door up for a little bit of error. So once again, that's something you need to be aware of. And it's important to remember this then ties into our curve aliasing. So you need to alias d phi versus d phi sandstone versus d phi dolomite differently. Same for the neutron. And in some cases, especially with things like neutron, these are vendor specific corrections. So if you really wanted to be 100% correct on this, you would need to alias at the vendor level before doing that conversion. So that's another consideration there. And making this decision really depends on the level of accuracy that's needed for your analysis. Okay, and then finally, just want to touch briefly on curve compositing. So once you've got your data aliased, all your units are consistent, everything's in a common lithological framework, then we're ready to start compositing the logs together. So aliasing, once again, this is important. It tells us what we need to composite together. And it's important to remember that, everything needs to be consistent before we do that compositing. If you composite curves with mixed units, then you're going to start having errors. If you mix, let's say, a density processing and bulk density together, that means if you try to apply an equation to that, you're going to be wrong. So it's important to remember that things have to all be correct and consistent before we composite things. Otherwise, we can't do downstream operations on them. And once we've done that, then we have kind of what I would call phase one outputs, where our data have been preconditioned to meet this 4C requirement, where we have clear and consistent names, consistent units, a consistent lithological reference, and a complete data set. The next step is we need to make the data clean here. And so we've handled now the structural problems, the data attribute problems. Now we're going to look at some of those data quality problems. So one of the most common data quality problems has to do with the scale of the data. And this is often addressed through the process of curve normalization. Curve normalization can be done in a number of ways. We can have shift operations. So this is where we just bulk shift values by either adding or subtracting a certain amount. We can either shift two curves to align with each other, and that would be a relative shift, or we can apply some absolute shift. Maybe we, shift the value by 3 units of whatever its value is. There can be 2-point operations. So these are stretch and squeeze operations. This could either be something like min-max scaling, or we stretch or squeeze the distribution from one well to match the distribution from another well. And we can even do, 3-point operations where there's a stretching, a shifting, and a squeezing. This can obviously be asymmetrical. And when doing this, you need to think about what are the consequences. Could this be too aggressive? And there's always a question of when should we normalize and what should we normalize? So when to normalize your data? Well, if you have such a large amount of data that you're not able to go through and set parameters on a zone by zone, well by well basis, normalization is something you should consider. You should also consider normalization, when your data ranges are relatively similar. And normalization is a way to effectively deal with some of the variation that's caused by multiple vendors or different generations of tools being inside the same data set. And from a practical point of view, definitely normalize your data if it helps you with performing correlation. You can normalize that data, perform your correlation, and then you can turn off the normalization after you've got your framework built out, for example. You should not normalize, when you have facies or geological driven changes in your log data. So if you have 2 logs and they have a different data range, the question should be, is that change real? And if that change is real, you do not want to normalize that away. Normalization can also be made tricky when you have differences that are caused by compacted and uncompacted sediments. So maybe when performing that normalization, you only want to look at, things that are like for like. So only looking at, compacted sediments, for example. Normalization is not a substitute for unit conversion. So, for example, if you have one well in percent and one well in decimal, you should convert to a common unit and then normalize instead of trying to use normalization to do that conversion for you. That's just a bad practice, but it is something where I often see people doing that, so I feel like it's worth addressing. And normalization is not a way to fix bad data, such as washouts. That, once again, is a separate process, and it should be done independently. Okay, and then the question of, what to normalize. Well, any data can be normalized. You can normalize any and every piece of curve data that you want. I will say that gamma ray is the one that we see most commonly normalized. However, I do see people use this on basically everything. I would, however, urge some caution when normalizing things like the resistivity, because that generally has a logarithmic type of response. So you would generally, if normalizing that, want to consider utilizing a method that can account for the logarithmic nature of the data. So when can normalization go wrong? Well, if you have bad or errant data points, this can certainly create problems with normalization, especially if you're doing something like min-max scaling. Remember, if you're doing true min-max scaling on your data, one bad data point can completely throw off your normalization. That's why I never do a true min-max. I normalize based on some percentile. Remember that if you have like some erroneous null values that are in there, or a poorly normalized point, that can also create some problems in normalization. Also, remember, uncompacted sediments often have quite a different response than compacted sediments, and often in very shallow depths in a log, you'll notice, like, you'll see a distinct shift in things like your density and your sonic curves, your neutron response, and so you need to make sure that you think about that when you're starting your normalization, and how you're gathering statistics from your wellbore to perform that normalization. So just something to be aware of there. And then the other part of getting your data clean is identifying, where there is bad holes. So where do have the wellbore conditions resulted in a log response that misrepresents the subsurface? Density is what we normally think of in this case, and that's because density has a very shallow depth of investigation. So even small problems in the borehole can affect the density curve. And what goes alongside of this is recognizing what curves are more reliable. So things like the neutron curve and the resistivity curve, these have deeper depths of investigation. They are therefore more robust to washouts. And so, even though you may have a poor response in one curve, there's still data that is available to you from other curves in many cases. And it's also just an important reminder that we're not on, you are identifying areas that have a bad response, or an abnormal log response, and then wells that have a kind of an expected response. And sometimes it can be difficult to determine the difference between what is abnormal data and what is data that is just rare. So for example, if you're looking at the density curve and you see a zone where the caliper doesn't respond, but maybe you have a density of, like 1.8, 1.9, that could just be telling you that you have a coal layer there, or maybe a salt layer. So, make sure to take care not to mistake low density minerals for washout. Otherwise, you may be removing some geology, removing some real data from your analysis. So there are a number of ways that we can identify Badhole. One of the primary methods is, just looking at caliper. We can apply caliper cutoffs, and we can say, hey, if the caliper is greater than a certain value, then, the log response is suspect. Now, when doing this, we have to consider the bit size. Having the caliper read, 14 inches, that may be just fine if you're in 13 and 5/8 inch hole, but that may be an egregious washout if you're in 9-inch hole. So whenever you're looking at caliper, you have to look at bit size as well. For the density curve, we often have a D-row or density correction curve. This is specific to the density tool, and often when you see high values on the D-row, that is a sign that the corresponding density curve is not reliable. So we can look at things like that. And then we can also look at wellbore rugosity. What's the rate of change of that wellbore? And this is a way to try to remove a little bit of the bit size concern from things like the caliper. And we can also look at, cross plots. So, can we identify erroneous data by looking at the correlation of one curve relative to another? So let's look at an example of Badhole. So, here, we've got a well log from the Alston Chalk. And, here we have a couple of very obvious washouts here. And we can see that a couple of different things. One, as we have different lithologies, we probably want to set absolute cutoffs different. So, if we want to say what is a bad density response just based on the value of the density curve, obviously we would set that different here in the Eagleford than we would in the Alston Chalk. When looking at caliper, we need to remember, what is the bit size? Was there a bit size change here that would set a different baseline for that? So we need to set these parameters on a zone by zone basis in many cases. And we need to evaluate what data is good and what data is erroneous. So, in almost all the cases, our gamma ray response is going to be accurate. Our neutron response here is quite stable regardless of the hole condition, so that's probably something reliable. And if we look over here at our sonic log, we can see that our sonic log is good, and where we do see spikes in the sonic log, we also see corresponding spikes in the gamma ray. And this may be telling us not that the washout is affecting the sonic, but that this is an actual lithological change driven by shells. Whereas the density curve, with its shallow depth of investigation, we see extreme values here that are erroneous. We do not have, 25 or 30% porosity here. We instead have bad data that needs to be corrected. Also, with that data, what you'll often notice is that there are some edge effects here where, as we're coming into and going out of the washouts, if we were to exactly draw our cutoff here, there's probably a couple of depth steps of washout that, we're missing here. And so we often need to pad out our Badhole flags to account for that. I also mentioned that you can identify Badhole from cross plots. I will say that, this works quite well when done on a single well, but when working with multiple wells, I find this to be more and more challenging. The idea is essentially that you want to, uh, highlight the data, via some region um, that we believe is erroneous. Um, so for example, in this case, I'm looking at where do we have an abnormal density response relative to the neutron. And you would need to think about, hey, is there gas effect, or is this actually due to a poor density response? And this is something that you need to do really on a zone by zone, well by well basis. Um, and I will say that this becomes more and more challenging as you have mixed lithology systems. You really need to subdivide in this case. And it's often important to try multiple crossplots. So, neutron density is only one example. Look at other crossplots as well to determine if others may work better in certain areas or with certain curve suites. So once you have identified Badhole, what do you do with it? Well, you can either null out the data so that it doesn't get used in future calculations. Now, the problem with this is that means you're going to have gaps in your interpretations. You can try to use alternative methods. So for example, if your density is washed out, maybe you switch over to a sonic porosity. This can also create some problems. It means that you need to calibrate one method against the other to make sure that you're consistent. And also, you may only have access to the data that you would need for those alternative methods in a small number of wells. So, you may only have sonic porosity in half the wells that you need it for. So once again, this may result in a sparser interpretation. The other option is you can try to reconstruct the curves. So we can essentially use some curve-to-curve relationships, and this could either be something like the Gardner relation, or it could be something like multilinear regression or some other type of machine learning model used to predict log values. And with either of these methods, you just really need to understand, what are the range of uncertainties there. So, for example, here we're looking at the Gardner relationship. I think, this is something that can work quite well. It's straightforward and it's easy to understand. It's easy enough to calibrate. But it is lithology dependent. So here in this example, the black curve represents the Gardner relationship, and you can see that although it would work exceptionally well in the Alston chalk, we do have some questions about it in our shell intervals, and we need to pay careful attention to the calibration there to feel comfortable with it. And really, this type of one-to-one correlation only works, if you have high quality data and it's quite consistent across an area. Machine learning, I think, can be a bit more robust in terms of, repair methods in washouts. We can use things like multilinear regression. We can use the ensemble methods like random forest or gradient boosting. We can use neural networks. There's a number of ways that this can be done. Machine learning models, they do require good data for training. They often require a lot of data, so you need to make sure that you have enough good quality data to build the model and to test its accuracy. And, are the intervals that you need to repair, are they adequately represented by the training data that you have available? So that's always a good question. And the data needs to be consistent. So if you build a model that requires, inputs A, B, and C, that the model can't run unless you have A, B, and C. So if you're missing one of those, you'll have to fall back to an alternative model. So that's important to consider. And obviously, you need to think about model accuracy and repeatability. Remember, it's very possible to overtrain machine learning models to where you get very specific results that aren't, broadly applicable. And you need to understand the range of uncertainty and the impact that'll then have downstream on your interpretation. So when thinking about machine learning, so what curve suite to use, that's something that needs to be considered. You also need to consider what happens if the curve suite varies from well to well. And what even if the curve suite varies within a well? So for example, you may only have a sonic log over a portion of the well, or there may be areas where the washout is bad enough where it actually affects your sonic log, so you would not want to use that in your reconstruction. So that's a consideration. Um, you know, so one of the things that we like to think about is building multiple models and then applying the best model. So for example, what I'm trying to show here is that, if you're repairing a density, maybe you start off, trying to use the full suite of curves. And then you build, every combination of model that's available, and you train, test, and then apply the best available model. Now, obviously, doing this by hand is impossible. With a full curve suite, you may have 10, 15, 20 models that you could run. And the thing is, you need to do this in an automated fashion if you're going to do it at scale. So here we can look at a data here. What I'll say is that the training data should almost be perfectly reconstructed. You should see a one-to-one match between the training data and the prediction that you make when using training data and the actual data. Thin washouts usually get very well handled very well. And the thicker intervals, of consistent washout, these are the ones that are hardest to predict. But if we have similar lithologies that aren't as affected, we should still see good washouts. So here we have large portions of the chalk that are washed out, but we also have areas with no washout that we can use to build that correlation for the machine learning model. Okay, and so that kind of finishes the second part of our two-phase cleanup. So now we have modified the data to have consistent ranges, and we've reconstructed the curves to be representative of the subsurface. So now we have truly satisfied all the criteria in our 4C framework. So I really quickly want to talk about how we do this in Danomics. So we have focused a lot on automation and having things available to the interpreter right off the start. So we have a pre-built alias table of nearly 7,500 curve mnemonics at this point. We have built-in methods to automatically read your curve units, evaluate statistics, and apply conversions as needed. We use our curve mnemonics from the alias table to evaluate the lithological reference and perform conversions automatically. So we'll take those disparate types like density porosity sandstone, density porosity dolomite. We will, we alias those separately. We evaluate them separately before converting them back to a bulk density. And so everything, so we try to handle everything automatically before we do that compositing. And that's all done in the background, really, with no user interaction necessary. We also focus on giving the interpreter easy access to normalization. So we do both relative and fixed value scaling within Danomics. So this is easy to do, and we have it set up for like one-click normalization where you just select the method. How do you want to do this? Shifting, scaling, three-point scaling, etc. So we've tried to make this where it's literally just the click of a button to have all your wells normalized. We also have options for performing spatially based normalization. And this is a method that allows you to perform normalization without removing the overall geological trend within your data. And when it comes to Badhole ID and repair, we give you a number of different methods to identify washout and to set criteria there. And then we have the automated Badhole repair via machine learning, where you can either use multilinear regression or random forest. Okay, so I know that was a lot in here, but I think it is worth putting some thought into getting your data interpretation ready. Like I said, if you don't think about having interpretation ready data, that means every time you go to start a new project, you are going to be repeating a large amount of work, and your very well paid subsurface interpreters are going to be spending 2, 3, 4 or more weeks dealing with a lot of this data management, data conditioning type of work, as opposed to actually going out there and developing new prospects, identifying new plays or new areas to be drilled. So it's important to get your data interpretation ready as quickly as possible, and it's best when this is done as part of an applied workflow that can be done in a consistent manner. And that is something that I think Danomics offers. And I would be happy to show you the results of how this works in Danomics and walk you through some examples of how we can do this and see if it can help you reduce your project startup costs. For more information, you can always find our website at www.danomics.com, or you can email me at csnow@danomics.com, and I'll be happy to get back to you. And if you'd like to give the product a try, when you go to our homepage, you will see a button here to create an account, so you can register yourself for an account. We just ask that you please do that with your business email address. All right, I hope this webinar has been useful to you. Once again, if you have any questions about getting your data interpretation ready, feel free to reach out to us. Thank you.